Hi there. So the next thing that I'm going to talk about is sections 5.1 through 5.3. One quick comment to make, sections 5.1 and 5.2 there's no homework for. Those are just reading assignments to kind of give you the general background scoop of what's going on. In section 5.3 there are actual homework assignments. So a reasonable question to ask is, what are we doing when we compute these antiderivatives? We've practiced, we've done substitution method, and we've found the antiderivatives of many different functions, okay? But what is it that we're looking at? Well, that's what we're going to talk about here, okay? And this gets to what we call the area problem. Essentially, what we want to do is find the areas of irregularly shaped regions. This comes about very frequently. If any of you have studied, for example, normal distributions and talked about the area under the curve, that's one of those things that we're looking at, okay? So I just drew this function randomly. This is my function f of x, and suppose I want to find the area bounded by the function and the x-axis between x equals a and x equals b, okay? It's an irregularly shaped region. So we need to ask ourselves, how can we find this area, okay? We know how to find the area of various polygons, but we don't know what's going on here. So what we want to do is say to ourselves, all right, let's go back and do something that's familiar to us. And I think you'll grant me that one thing that's quite familiar to us is finding the area of rectangles. The area of a rectangle is length times width or base times height. So one thing that we could do is we could say, well, why don't we estimate this area by drawing rectangles? So one of the things we could do is subdivide this region where all of these lengths are evenly spaced, okay? And then what we could do is draw rectangles. Presumably, if we know our function, then we'll know the height of the rectangles. Now, one question to ask is, okay, let's suppose we do draw rectangles. How high should you make them? Should you use your left endpoint? Should you use your right endpoint? Should you use a midpoint? Okay, well, I think you'll grant me, for example, if I use left endpoints, this is going to be what they look like. And let's just assume these are actually straight lines that I'm drawing. And finally there. Okay, now this is a pretty decent estimate. The height of each rectangle is my function value. So if I use my left endpoints, I've got my function values for my left endpoints. And presumably each of these distances are the same. And we can find the area. This one goes over a little bit, these go under a little bit. So perhaps we could think that this is perhaps an underestimate. But it's still a pretty good estimate. Now, you could say, well, why don't we try to use right endpoints? We can certainly use our right endpoints to find the height of each of these. And what we're going to get here is an overestimate. Again, the area of each of these rectangles is this length times my function value at my right endpoint. Okay, so using rectangles is sort of the idea that we're going to want to go on. Okay, and again, the area of each rectangle is this length times my function value. Now, I think you will also grant me that perhaps if we use the midpoint, we might get a better estimate. Something that some people do is say, well, why don't we compute some of the areas of the rectangles using our left endpoints and then use our right endpoints and then take the average of the two. And that can be a pretty good estimate, okay? So what I want to say is this. If I make a certain number of rectangles, okay, but then suppose I say, well, let's make more and more rectangles. In other words, we're going to make this more and more precise, whether we use our left endpoint or our right endpoint. The more rectangles I make, the more precise those areas of the rectangles are going to be to the area under my function. Okay? So essentially what we want to do is use rectangles, find the sum of the areas of those rectangles, and add them up. Okay? So our basic setup is as follows. If y equals f of x is a continuous function on some closed bounded interval, say from a to b, then what we do is we fix a positive integer n that is going to give us the number of subintervals. In other words, the number of rectangles that we're going to be using. And I claim that the length of each subinterval we'll call delta x, and that's equal to b minus a over n. In other words, each of these rectangles has the exact same length, if you will, assuming we subdivide them all again, and they all have length delta x. Okay? So, what we then do is we call these guys various partition points, and what we want to do is find the area of each of those rectangles. So, for example, suppose I have the following. Suppose A is my left endpoint, and then I have x1, x2, all the way up to b. Okay? Well, what's going to be the area of each of those rectangles if we use our left endpoints? We're going to have this length here, and let's just talk about our left endpoints times our first function value. That covers this rectangle. Now we'll cover this next rectangle. Delta x times my function value at the left endpoint. And I keep going on and on and on, and up to my last endpoint. Okay? Well, one of the things we can do is we see we have a delta x. We can factor that out, and then I claim I'm just adding up all my different function values. Now, as you know, in mathematics, one of the things we like to do is use notation. Okay? That's a lot of writing. So what we essentially come up with is we say this is delta x, and when you're taking the sum of a whole bunch of things, we use a capital sigma. That's saying we're taking the sum of the function values, well, from I equals 0, essentially to n minus 1 here. Okay? So, what did we do? What we did is we said, let's estimate the area under this curve by drawing rectangles. Okay? Now, if you have an increasing function, if you use the left endpoints, you're going to have an underestimate. On the other hand, if you have a decreasing function and you use left endpoints, you're going to have an overestimate. So, this is the basic idea of what we're talking about right now here, looking at the areas. We want to say to ourselves, okay, let's find the area of each of those rectangles, and then let's add them up. Okay? So, what we want to do then is formalize this. Okay? Before I formalize it though, what I would like to do is take a very common function that we have. Let's take y equals x squared, and let's just look at it from 1 to 2. And let's further say, let's let n equals 4. Okay? Again, this is nothing that you're going to need to do per se in this class, but it gives you some background ideas. Okay? And this is super cool. So, let's check this out. We can certainly draw the graph of y equals x squared, and if we're looking at it, say from 1 to 2, This is the region that we want to find the area of. Now, what we're saying is we want to separate it into 4 different rectangles. So here we have 4 different rectangles. And if I draw these rectangles using my left endpoints, it's going to look something like this. Notice if I find the area of each of these rectangles and add them up, it's going to give me a big underestimate, isn't it? Essentially, I'm missing out on all of this area that does take part. But let's see what we get if we actually do this. Okay? Well, how would we find the area? First off, we need to know what each of these subintervals have a length of. And again, we have delta x is b minus a over n. So we have 2 minus 1 over 4. So each of these guys have a length of 1/4. Okay? So what is the area of my first rectangle? Well, it's 1/4 times my function value at 1. I'm using my left endpoints. Plus 1/4. Well, if each of these are length 1/4, that would be times my function value at 1.25. Plus 1/4 times my function value at 1.5. And finally, plus 1/4 times my function value at 1.75. And using what we had right over here, we can essentially say, yeah, we can factor out the 1/4, and we're finding our function value at 1 plus our function value at 1 1/4, function value at 1 1/2, and our function value at 1.75. Okay? Can we find those function values? Absolutely. Okay? There's my function. So essentially, what I have is 1/4 times 1 squared plus 1.25 squared plus 1.5 squared plus 1.75 squared. Okay, where did I get the squared? I plugged it in to get my function value. And what we see is that we're going to get 1.969. And we know that that's an underestimate. Okay? Now, suppose you said, well, let's use our right endpoints for each of these. If I use my right endpoints for each of these rectangles, you'll see that I'm getting quite the overestimate. Okay? Now, instead of missing a bunch of region, I have a lot of excess region. So let's see what we get there when we do this computation. Well, what I'll do is I'm already going to pull out my 1/4. Now, what is the height of my first rectangle? It's my function value there, f of 1.25 plus f of 1.5 plus f of 1.75 plus f of 2. And we can plug each of those values in to square them, and you'll see we get about 2.719. All right, so we know that this is a lower estimate. We know this is an upper estimate. So if we take the average of them, what we get is about 2.344. Okay? So this is what we're looking at when we draw rectangles. Now, a couple things that I want to point out to you. Okay? Let's jump back to chapter 6, back forward, right? Okay, what if I asked you to compute the definite integral from 1 to 2 of this function? Okay, how would we do that? Well, again, first thing we do is we would take the antiderivative of x squared, which is x cubed over 3, and we would evaluate that from 1 to 2. In other words, we'd plug 2 in and subtract off what we get when we plug in 1. So, what do we get? We get 8/3 minus 1/3, which is 7/3. and that's equal to 2.3 repeating. Okay? I alluded to this before when we were talking in chapter 6. Notice the average of those sums and what my definite integral turned out to be. Okay? And this is just with 4 rectangles. I claim that if we fine-tune this and do 8 rectangles and then 16 rectangles, however many rectangles, the more we do, the more precise this is going to be. Okay? So this brings us back to a topic of conversation that we had before about limits. Essentially, what we have is this. We let the number of rectangles go to infinity. Okay? In other words, we're looking at that limit as n goes to infinity. And it turns out if you take the limit as n goes to infinity of the sum from I equals 1 to n, in other words, of these rectangles, of your function values times the width of each of these, this approximates precisely the definite integral. Now, this is a definition. The definition is the definite integral from a to b of a function is precisely the area under the curve. Okay? This comes up so often that this actually has a name. They're called Riemann sums. If you were in a regular calculus class, we would be spending a lot of time talking about Riemann sums, and we would be doing a lot of these rectangles. But the idea behind this is when you're taking a definite integral, what you're doing is you're finding the area bounded by that region. Okay? In this case, it would be between this region and the x-axis from x equals a to x equals b. It's precisely that area. Okay? Now, here's something that's really important to point out. When you're computing an antiderivative, suppose, for example, taking a very similar function, suppose I want to compute the integral from 1 to 2 of negative x squared dx. Okay? Something that I want to point out. If you're looking at negative x squared from 1 to 2, this is the area that we're looking at right here. Okay? Now, what do we know? What we know is that when we're computing these definite integrals, it's the area of the region, and the way that area is computed is precisely the length of each of these subintervals times your function values. But notice, my function values here are negative. Okay? So, what we're going to get actually is a negative answer. Okay? If you compute the antiderivative here, you get negative x cubed over 3. And again, we want to evaluate that from 1 to 2. I got to find a better marker here. So we plug in 2 and subtract off what we get when we plug in 1. We get negative 8, over 3 minus a negative 1 over 3. Minus a negative is plus a positive. So notice we get a negative 7/3. Okay? When you compute a definite integral and you get a negative answer, the reason why is because those function values are below your x-axis, and therefore that's going to be the function value that you're computing here. Okay? That's a really important thing to keep in mind. All right. So, that's the main idea of what we're talking about here. And now that we've established, so that's what you're going to read about in more detail when you read through sections 5.1 and 5.2. Okay? But now what we're going to do is we're going to say, all right, we have the integral from a to b of a function is precisely the area bounded by your function and the x-axis from x equals a to x equals b. So, for example, how would we find this? What if I wanted us to find the area bounded by, let's just take y equals the square root of x from x equals 1 to x equals 4, bounded by that and the x-axis. Okay, so if you're asked to find an area, what the connection you've got to make is that you're computing the definite integral. We're computing the definite integral from 1 to 4, and my function is x to the 1/2 dx. Okay? So, first thing we do, take the antiderivative, we add 1 to the exponent, and then we divide by that, which is 2/3 times x to the 3/2 power. Okay? Now we evaluate that at 4 and subtract off what we get when we evaluate that at 1. So what do we have? We have 2/3 4 to the 3/2 power minus 2/3 1 to the 3/2 power. Okay? Now, going back to our exponents, when you have something to the 3/2, the way you look at it is it's to the 1/2 and then cubed. So it's 1 to the 1/2 and then cubed. Well, what's 4 to the 1/2 power? That's the square root of 4, which is 2, and 2 cubed is 8. So you get 2/3 times 8, or 16/3, and minus 2/3, so the area is 14/3. Okay? Now, on the other hand, what if I wanted us to find the area bounded between two curves? Okay, so I'm just going to change this slightly here. What I'm going to say is, suppose we have two functions. Here's f of x, and here's g of x. And let's suppose we want to find the area bounded between those curves from A to B. How would we find the area of this region? Well, I claim it's very much the same as what we've been doing. Okay? One thing you could say is, well, we could take the definite integral from A to B of f of x. Okay, and if we did that, then not only are we getting that region, but we also have all this down here. Right? Between f of x and the x-axis, we have all that excess region here. But we don't want that region. So we ask ourselves, how do we get rid of that? Well, we know mathematically what we would do is subtract off this area. Well, by definition, isn't the area right here between this function and my x-axis the definite integral of g of x? So, the way you compute the definite integral, the way you compute the area between two curves, is you compute the definite integral, you take the function on top minus the function on the bottom, and evaluate as usual. All right, so what I want to do now is just play with a few examples here, okay? So the main gist of what I want you to get from this is that when you're computing a definite integral, you're finding the area under the curve, okay? So a couple examples just to get us comfortable with everything. Let's look at this. What if I want us to find the area between, how about y equals x squared and y equals x cubed for x between 0 and 1. Okay? So we know we want to find the area between two curves. That tells us that we're going to be computing a definite integral. The question is, between 0 and 1, which function lies on top of the other? Well, let's look. When x is equal to 0, both of these guys are equal to 0. When x is equal to 1, well, 1 squared is 1, and 1 cubed is 1. So at this point, we don't know. So what you do is you take some value in between and you plug it in. So for example, 1/2 is probably the nicest number to take. If I plug 1/2 in here, I get 1/4. If I plug 1/2 in here and cube it, I get 1/8. So that tells me that y equals x squared lives on top of y equals x cubed. So this little wedge is what I want to find the area of. So how would we compute that? Well, it's the definite integral from 0 to 1. We found that x squared is bigger in the region between 0 and 1. So we put him first. All right, let's do it. What do we get? Take the antiderivative, we get x cubed over 3 minus x to the 4th over 4. And I always celebrate when I have polynomials and I get to plug in 0, because you don't have to worry about anything. So we take f of 1 minus f of 0. If I plug in 1, I get 1/3 minus 1/4. And I claim if I plug in 0, I just get a 0. So what do we have? We have 4/12 minus 3/12. So the area is 1/12. Now, if we had mixed those up and we thought that x cubed was larger, what you would end up getting is a negative 1/12 here, and that should be like a red alert that you mixed them up. Okay? So let's look at this one now. What if now I want to find the area bounded by, how about y equals x squared and y equals 3x? Now, something that I want to point out is, notice I didn't give the endpoints here. So what do you do if no endpoints are given and you're just told to find the area between two regions? Well, what I would do is I would first think about a graph, okay, to figure out what these functions look like. And we're very familiar with our parabolas and our lines. But when no endpoints are given, what you do is you say, well, we want to find the area bounded between these two curves. Let's see where they intersect and find the area between those regions. So how do you know where these two curves intersect? Well, you set them equal. And is this something we can solve? Totally. Scoot everything to one side. And you can pull out an x. And now we have the product of two things equal to 0. So either the first one is 0 or the second one is 0. and those give us the values. And I think you'll grant me that if I plug 0 in each of these functions, I get 0. And if I plug 3 in each of these functions, I'm going to get 9. Okay? All right. Now, we can ask, who lies on top of the other? Well, let's just take a random point between 0 and 3. Okay? So if I take 1, he's bigger. If I take 2, he's bigger. So I know that my line lies on top of my parabola. Okay? So now that we found those values, we can compute our definite integral. What are we going to look at? We're going to look at the integral from 0 to 3. Since 3x is on top, we do 3x minus x squared dx. And now we can go through and compute this as before. Take the antiderivative of both terms, and we're looking at that from 0 to 3. We erase this so we don't get confused. All right, so we plug in 3, and then we subtract off what we get when we plug in 0. Well, if I plug 3 in here, I have 3 squared, which is 9, times 3 is 27. So I have 27 halves minus, well, 3 cubed is 27 over 3. 27 divided by 3 is 9. And then if we plug 0 in, again, we get 0. So 27 halves minus 9, we're going to get 4.5. Cool, huh? All right, let's now do this. Suppose now I want you to find the value of b if the area under the graph f of x equals 4x between x equals 1 and x equals b is 240. And we're going to also make an assumption that b is greater than 1. These are really cute types of questions. Okay, what do we do here? Well, first off, we know our function. We know it's a line with the slope equal to 4, and we're interested in it from 1 to b. And we know that this area is 240. Notice we're assuming that b is larger than 1. So let's set up what we have and what we know. What do we know? We know that we're wanting to find the area from 1 to b. We know the function that we want to find the area under, that's 4x. And we also know that it's equal to 240. Do we have enough information to solve for b? Absolutely. Okay, let's go through and do this. What can we do here? The first thing we would do is take our antiderivative. You get 4x squared over 2. Therefore, my antiderivative is 2x squared. We're going to evaluate that from 1 to b, and we already know that that's going to be equal to 240. Well, what do we get when we evaluate it from 1 to b? Well, f of b minus f of 1. So that's 2b squared. And if you plug 1 in here, you're going to get minus 2 is 240. Is this something we can solve? Totally. Okay, I can add 2. I get 2b squared is 242. Divide both sides by 2. We get b squared is 121. And how do we solve for b? You take the square root of both sides. And yes, you get positive and negative 11, but notice we're assuming b is greater than 1. So our answer is 11. Isn't that fun? All right. So one other example that I would like to do with you is as follows. Suppose I give you this information. Suppose it's given that the definite integral from -1 to 0 of my function is 0.25. Okay? And we're going to have to make some serious assumptions here because I'm not very good at drawing these things. But let's suppose this is my function, f of x. And the assumption that we're going to make is that it's well drawn and that it's an odd function. In other words, what I want to assume is that this side is a mirror image of this side. Okay? In other words, those guys are the same. Remember, an odd function is one that's symmetric about my origin. Okay? So, assume it is an odd function. All right. Well, if we assume it's an odd function, here's what I want us to do. And I'll put a smiley face there. What if I want us to find then the integral from 0 to 1 of f of x dx? And then what if I want us to find the definite integral from -1 of f of x dx? And then what if I want us to find the total shaded area? I think that this is a great closing example because it just kind of hones in on the definite integrals and what you're actually computing. Okay? So what are we given? We are given that the area of this region is 0.25. Okay? That's what we have here. So notice it makes sense that it's positive because this lies above my x-axis, which leads me to exactly what I want to get at here. What if now we want to find the definite integral from 0 to 1, in other words, of this region? I said they were odd, so this is symmetric, but notice since this is below my x-axis, we would say it's negative 0.25. All right, now let's do this next one. Now we want to know the definite integral from -1 to +1. Well, this is positive 0.25. This is negative 0.25. So you know what we get for the definite integral? We get 0. Now contrast that with me asking you to find the total shaded area. When I ask you to find the total shaded area, what you want to think of is absolute value. And in that case, our solution is 0.25. It's this shaded area, which is 0.25. It's the absolute value of this shaded area, which is 0.25. So we get 0.5. Pretty cool. All right. Thank you.